So we're going to have a look at acids and bases. This would be Unit 10, Chapter 16 in your text. We are looking at some basic information here. Um, there is a little bit of background that you would probably need to go through the general idea of what an acid is, and that's all within Chapter 16 in your text. And those are the definitions of an acid and a base, both definitions. The definition of a conjugate acid and of base pairs, and then finally the properties of acids and bases. I will try and explain those a little bit as we go through, but the general idea is that you have read that section. So going back right to the start of the course, we have the idea of a strong acid and strong base. A strong acid or base is a compound that will dissociate completely, 100% ionization, or in other words, a strong electrolyte. More specifically, an acid is a compound that releases an H plus in solution. Um, so when we look at these two examples, hydrochloric acid, which is a strong acid, it's one of our seven, will completely break into H plus and Cl minus. A strong base does exactly the same thing, but increases the concentration of OH negative in solution. We've already covered that in the course, but an acid is a proton donor, and a base can be considered as a proton acceptor. Again, working at those definitions of an acid and base. And this is a proton acceptor in the way that OH will accept a proton to form water. It'll be HOH or H2O. That's the product. So we have seven strong acids. This list is something that you would have to know and be able to recognize. The bases that are very common are listed here. Sodium hydroxide, lithium hydroxide, and potassium hydroxide are probably your most common strong bases. But basically, it's hydroxides bonded with group 1 or some of the heavier group 2 cations. So it's the only way to really identify them. The big giveaway is that they do have OH in them. Um, Calcium hydroxide is a little weaker than others, but um, again, bases are just look for the OH, but acids, it is that list of seven. So in order to measure how acidic or how basic something is, we use a scale called the pH scale. pH stands for potential hydrogen. And it is a measure of acidity. It is a 0 to 14 scale, where the lower the number, the more acidic the compound is. So a 0 is incredibly acidic, and a 14 is very, very poorly acidic. In other words, a 14 is very basic. In the middle, we have 7, which is considered a neutral compound. pH is a logarithmic scale, which is defined by this equation. It says pH is equal to the negative log of the concentration of H plus. So looking at that, we basically are telling you when we give you a pH what the concentration of H plus is. So for example, if you have to balance the water in a pool, you're looking for a pH of 7.3. What that number represents is actually the amount of hydrogen ions in solution. So let's look at example 1. If a 0.20 molar solution of HCl is created, what is the pH? Well, first of all, HCl is on our list of 7 strong acids, number 1. So we know that HCl will completely dissociate into its ions, and this is aqueous, aqueous, aqueous. That's important because otherwise we're going to be dealing with an equilibrium situation, but right off the bat, we should be able to see that this is much more straightforward. If I have 0.20 molar of this, I'm going to have exactly the same concentration of H plus and Cl minus once it is basically in solution. So pH is equal to the negative log of the concentration of H plus. pH is equal to the negative log of 0.200 molar. So hit 2.2 log, hit the negative sign. The pH is 0.699, and there are no units on a pH. So it is 0.699. And that's pretty much as straightforward as it is. The only way this really gets complicated is when the concentration of H plus is not from a strong electrolyte. It's going to be from something that's weak, like a carboxylic acid or some sort of other organic acid. So we have two very simple problems. It would be helpful that as you go through this video to pause and try the questions as you go, so you actually have a chance, and then hit play and then go through the question with the recording. So it says a 0.0015 molar solution of HBr is placed in a flask. What is its pH? So HBr is a strong acid. It's going to break into its two ions. Again, all aqueous. pH is equal to the negative log of the concentration of H plus. So 0.0015, hit log, take the negative, is 2.82. We should check for significant figures. We only have 2, is 2.8. The pH of that solution is equal to 2.8. We can do the exact same thing. HCl is another strong acid. So as we look at this, we're looking at a solution of 1 mole per liter. So pH is equal to the negative log of the concentration of H. And one thing we should notice is that when you take the log of 1, you get 0. So 1 molar solution has a pH of 0. Now, the use of pH is very, very helpful because it actually gives us concentration in moles per liter. So we have to be able to go backwards from pH. So if you were given a solution of a certain pH, you can determine the concentration of H plus in solution by using that the concentration of H plus is equal to 10 to the negative pH. In other words, we're just going to use the opposite of log to do that. So if a solution of HCl has a pH of 3.0, what is the concentration of H plus in solution? So going backwards is a lot easier because considerations of equilibrium aren't really that important, because it will just tell you what the equilibrium value for H plus is, which is actually very, very helpful. So the concentration of H plus is equal to 10 to the negative pH. The concentration of H plus is equal to 10 to the negative 3.0. If you have a pH that's right on a particular value, it's very easy to deal with. So 3.0 turn it negative is 1.0 times 10 to the negative 3 moles per liter. And that is essentially how that's done. If it is a number right on, like 3.0, 4.0, it is just 1.0 times 10 to the negative of that pH. So it becomes very easy to do those conversions. And in sections on an exam where you are not allowed a calculator, it would be very, very helpful. So it says, what is the concentration of an acid solution where the pH is 6.9? So the concentration of H plus is equal to 10 times to the negative pH. The concentration of H plus is equal to 10 to the negative 6.9. So this one's a little bit more difficult because you have to actually put in a calculator, but is equal to 1.26 times 10 to the negative 7 moles per liter. And the same idea, what is the concentration of H plus in a solution where the pH is 12? So concentration of H plus is equal to 10 times to the negative 12. And basically you're just going to rewrite that. Um, that's a pretty obvious one. So 12. So if it's right on, you just have to rewrite it into scientific notation, essentially. So now we move on to the concept of a weak acid, which is why this is in this part of our course. It says if your acid is not one of the strong acids, it's considered to be weak. A weak acid is an acid that does not have a high ionization percentage and that does not completely break apart in solution. For example, acetic acid, which is one that we'll deal with a lot, is an organic acid, specifically called a carboxylic acid. So carboxylic acids are generally you have an alkyl group there, but it's the C double bond O and then OH group. So basically all of those are weak acids. When dissolved in water, it starts to break apart while other ions in the ions recombine to form acetic acid molecule. This is by definition an equilibrium process. So this molecule will break up into hydrogen and acetate, and then the acetate and hydrogen will recombine. We see that we are using Kc here, as we have in chapter 15, but when dealing with acids or bases, we have Ka for acids, and we use Kb for weak bases. It's just a little bit of notation that is pretty consistent across chemistry. So Ka is simply an equilibrium constant from the acid equilibrium. Since the equilibrium is constant is so much below 1, it shows the left side of the reaction is favored. So you'll notice that in weak acids, your Ka value will be very, very small. Never really bigger than 1, but 0.01 probably would be the highest for a weak acid that you will see. So basically, very, very small percentage of your H plus is going to break off. So we can continue by writing the equilibrium for this. So we have products, the concentration of the products raised to their powers over the product concentration of the reactant. And because most of the compound is going to stay as the reactant, it's not going to dissociate. The number will be very, very small. In this case, 1.8 times 10 to the negative 5. We can solve equilibrium problems now using this concept. We're basically just going to treat it as an equilibrium. Nothing really changes with the exception of we're going to be using Ka as a label instead of Kc. So it says, what is the pH of a 0.250 molar solution of acetic acid given the Ka is 1.8 times 10 to the negative 5? So we can write the equation out. And we know what the Ka is. And we have the equilibrium expression here, so we're not going to worry about rewriting that. We've done that, and that's not really the focus for this. So we are going to, however, bring out the concept of the icebox. So we'll draw out an icebox. Initial change in equilibrium. The one thing with acids, weak acids in equilibrium, is we can kind of cheat a little bit. So I'm just going to double line this actually so it shows up. We can kind of cheat because of how little of the acid is actually dissociating. So basically we'll start with 0 and 0. So we have no hydrogen, no acetate. And we're going to start with 0.250. Again, we are in big M, so we are in moles per liter, so we can continue. Now, here's the part that does get a little different. We don't know how much of this acid is going to dissociate, but it is 1 to 1 to 1 in this particular equation, so it's actually very straightforward. So 0.250 minus x, x, and x. So we have our expression. There's one little check that we can do that makes our life a lot easier. And there is a situation where if x is so incredibly small that any loss of x is insignificant, we can generally do a rule of thumb. And what we do is we say if the concentration of the acid, which we're going to symbolize by HA, divided by the Ka is greater than 500, we can ignore x. So in this particular case, we would have 0.250 over 1.8 times 10 to the negative 5. And when you do that calculation, you go 0.25, so that's the concentration of the acid. You can do this for a base, you can do this for any equilibrium, honestly. But you put the initial concentration of your starting product or material and divide it by your equilibrium constant. You'll see that it's equal to 13,000, let's call it 13,900. That is definitely greater than 500. What that means is that the loss of x is so small that even if when we do this operation, it's not going to matter. So I'm going to ignore x, and the only reason I'm allowed to do that is because the concentration divided by the equilibrium constant is greater than 500. It'll get close to 500, and sometimes we will take it into consideration, and it depends on how easy, how precise you want to be. It's never wrong to include it, but it does save us from a quadratic equation. So Ka is equal to the concentration of H plus so we plug in our values. 1.8 times 10 to the negative 5 is equal to x times x over 0.250. We generally can just write that as x squared. So I'm going to multiply 1.8 times 10 to the negative 5. I'm going to multiply that by 0.25. And I'm going to get 4.5 times 10 to the negative 6 is equal to x squared. I will take the root of both sides. So 2.12 times 10 to the negative 3 is equal to x. And that x is actually equal to the concentration of H plus. It also is equal to the concentration of the acetate, but I'm being asked for pH. So pH is equal to the negative log of the concentration of H plus. So log negative pH is equal to 2.7. And the pH is less than 7. It's an acid, so that makes sense. So now we have just a simple problem to try. We have formic acid dissociating into a hydrogen ion and a formate. We can write a general form for this. We can write HA goes to H plus plus A minus, where A minus just stands for the anion, and H is the acidic proton, which is this, and then A refers to the COOH in this case. And that makes the equilibrium expression pretty standard. Normally we should write what everything is. So let A minus equal the acetate ion, and then it looks pretty proper. So once again, we will quickly write out an icebox. So it says a 0.15 molar solution. We start with 0 and 0. We know we're going to lose x, x, x. So 0.15 minus x. So it's, again, it'll be very, very familiar. We can do the check here to see if we can ignore x. So you put the concentration in that you start with, 0.15, and you divide it by its constant. We get 833. Just because we are going through this as a sample, I am not going to ignore it. It is close. It is over 500, so there's no problem ignoring it. And you can go through and see that the answer should be very, very similar to what I get. So I'm actually going to use it though. So 1.8 times 10 to the negative 4 is equal to x squared over 0.15 minus x. So we're just going to make our quadratic equation. So 1.8 exponent 4 negative times 0.15 is 2.7 times 10 to the negative 5. And write it into quadratic form. So I have a quadratic form here. So I'm not really going to go through the quadratic equation. I'm just going to use a graphing calculator to solve it. So my x variable is 1. So that gives me two roots. Negative 0.00527 and plus 0.005107. So once you have the roots, nothing has really changed that much. That tells me the concentration of H plus is equal to X is equal to 0.005107 is equal to 5.11. So once you have this part solved out, pH is equal to the negative log of the concentration of H plus. Equals to 2.29. I only have two significant figures. pH is equal to 2.3. So now that we know how to use equilibrium to solve the pH of a question, we're going to look at some auto-ionization problems. So the auto-ionization of water simply says that water does not really exist as H2O. It'll exist as three different species: H2O, H3O plus, and basically OH negative. The autoionization means that it ionizes itself. So when you have two molecules of H2O, they will combine and form H3O plus and OH negative. This is an equilibrium process where the Kc at standard temperature is known as Kw for the water ionization constant. It is always this number that we basically use in chemistry. We always assume it's standard conditions unless we're given an updated version for a particular problem. And it's always 1.0 times 10 to the negative 14. When you write out the ionization of water, you'll notice that H2O is, of course, a liquid, and we do not include liquids and solids in equilibrium expressions. So we only are going to have products with nothing on the denominator. So Kw is equal to the concentration of H3O times the concentration of OH negative. H3O is called the hydronium ion, and basically it is an acidic proton. Um, it is usually simplified also as the concentration of H plus times the concentration of OH negative. So in other words, if you multiply in moles per liter the concentration of H plus times the concentration of OH negative, it has to equal 1.0 times 10 to the negative 14 in any solution. So that's very, very useful. So when you take neutral water, which is what water should be, but obviously rainwater is a little more acidic from the rain, um, and certain waters that have had a lot exposure to a lot of calcium, hydroxide and stuff will have be a little more basic. So kind of all over the place in reality, but in an ideal world, the pH of water is 7. So the concentration of H plus is equal to 10 times the negative pH. So in this particular case for neutral water, the pH is 7, so it's a negative 7. So that's the concentration of water. The concentration of OH just has to be whatever the is missing to make that product true. So we divide the Kw, 110 to the 14, negative 14, by the concentration of H plus, and that tells me what the concentration of OH negative should have been. It can get even simpler than that, because if we're just dealing with logarithms, we can say that pH, the potential hydrogen, plus POH, which is the potential hydroxide ion present in solution, which might be a new concept for you, but where POH is the negative log of the concentration of OH negative, pH plus POH has to equal 14. So anytime you have pH, you know what POH is, because if, for example, you had a pH of 2, then POH has to be 14. So it says determine the concentration of H plus in a solution with a pH of 5.3. Well, pH plus POH is equal to 14. 5.3 plus POH is equal to 14. POH is equal to 14 minus 5.3. POH must be equal to 8.7. The concentration of OH negative is equal to 10 to the negative POH. Concentration of OH negative is equal to 10 to the negative 8.7. 8.7 negative. And there we go. So that's very simply how we can control or figure out what the concentration of OH is in solution. There's always a balance in an aqueous solution because water is present, so autoionization is going to happen. So we have a couple try these here. It says what is the concentration of H plus if the concentration of OH negative is equal to 1.3 times 10 to the negative 5. The units aren't there, but we're going to assume it's moles per liter. We know the concentration of H plus times the concentration of OH negative is equal to the autoionization constant, or equal to Kw. So the concentration of H plus must equal the autoionization constant. Divided by the concentration of OH. Simply do this calculation. .69 times 10 to the negative 10 moles per liter. For part B, we have a situation where We are given POH, we're given pH. So POH is equal to 14 minus pH is equal to 14 minus 3.3 is equal to 10.7. Concentration of OH negative is equal to 10 to the negative POH is equal to 10 to the negative 10.7. 10.7 negative. I only have two significant figures again. And that is how we do the calculations. So it's very simple, very straightforward, but very, very useful. So we have two sample questions here, and it's just to sort of review what we have done. It says a sample of 0.250 molar acetic acid is prepared. What is the pH of solution? So quickly, CH3, COOH. So we have the acetic acid dissociating. We know that Ka is equal to H plus times the acetate ion. So we have here Ka. We know that Ka for this problem is 1.8 times 10 to the negative 5 from earlier. But we can look that up in Appendix D if we want it to in your text. We can simply do the test, but we can write out the icebox. Just a quick and rough icebox. So 0.250, 0. I'm going to lose x, I'm going to gain x, I'm going to gain x. So 0.25 minus x, x, and x. We can do our check. So remember what the check is. It's the concentration that you start with, 0.25, divided by the Ka. For acetic acid is 1.8 times 10 to the negative 5. We've already done this one because it's 13,888.8, which means it's much greater than 500. So I'm going to drop the x. I know that Ka is 1.8 times 10 to the negative 5. That's going to be equal to x squared over 0.250. Solve for x. So solving for x is pretty straightforward. 1.8 exponent 5 negative. Multiply both sides by 0.250. That gives me x squared. Take the root. Equals 2.12 times 10 to the negative 3. And that is in moles per liter. That is equal to the concentration of H plus as well. So finally, pH is equal to the negative log of the concentration of H plus is equal to the negative log of 2.12 times 10 to the negative 3 is equal to 2.67. So that's what A is. So again, if we could ignore x, we save ourselves a lot of time. For part B, POH is equal to 14 minus pH is equal to 14 minus 2.67 is equal to 11.3. Ignore significant figures here. And then finally, what is the concentration of OH? The concentration of OH negative is equal to 10 to the negative POH is equal to 10 to the negative 11.3. 11.3 negative is equal to 5.01 times 10 to the negative 12 moles per liter. So again, anytime you can ignore x, it makes the question a lot quicker. Otherwise, you're in the quadratic, and if you have a graphing calculator or a calculator that can solve the quadratic, it is, again, very straightforward anyway. So for the next question, we are being given nitrous acid, HNO2, which can be tricky because HNO3 is a strong acid, but nitrous is a weak acid. We're given the Ka at 4.5 times 10 to the negative 4, and we're given the pH. So first of all, let's write out the equilibrium expression. We'll start with an icebox. Now, the question in this particular case is a little different because we have to, we've been given a pH. So we know that the pH is going to be equal to 2.0. So that means the concentration of H plus is 1.0 times 10 to the negative 2 moles per liter. And that is the equilibrium constant value. And it's going to be equal to, obviously, the nitrate ion as well. So in this particular case, we're going to use Ka, which is 4.5 times 10 to the negative 4, is equal to the concentration of H plus times the concentration of nitrate over the concentration of HNO2. Now it's a little bit different, is we have the numerator completely, and we are looking for the denominator. We are going to lose a very small amount of this, but we can take it into account if we wish. So basically, I know that I lost how much I lost because of the pH. So I have my icebox all filled in. So 4.5 times 10 to the negative 4 is equal to 1.0 times 10 to the negative 2. I'm just going to write that as a square. So I'm going to multiply the denominator over. We didn't need to use a calculator for that part, but so 4.5 times 10 to the negative 4 x minus 4.5 4 negative times, I can't believe I used So we'll continue trying to isolate x now. 4.5 times 10 to the negative 4. X equals, so we'll add 4.5 to both sides. And you can see how little the x value is actually going to matter. So I'm going to divide both sides. X would be equal to 0.232, and that's moles per liter, and that's equal to the concentration of HNO2. So finally, 0.232 moles per liter times 0.550 liters is equal to 0.116 moles. Zero 0.116 moles of HNO2 figure out the formula weight of nitric acid nitrous acid. It's 1 hydrogen plus 14.007 plus 32 is 47.017 grams per mole times 0.11716 is 5.45 grams HNO2, which is the final answer.